I mean, I'm doing it from home. It's still quite early here, but actually my internet connection should be very good, so I'm not too worried about that.
Yeah. Well, it's wonderful to have this technology, but there is always a worry that it may not work when you need it most.
Yeah, and I mean, one of these days, I think, as I told you, I wouldn't mind visiting India, but at the moment it's still too crazy. But things may look a lot different in 2 years. That will be. Then I'm planning to just do research and not be bound to the semester and all this kind of stuff. So.
Yes.
It's always the problem with having to teach in between and meetings and whatever. There's always something.
Yeah, but you should certainly plan a visit to India and come down to Tirupati. Tirupati has these two institutions. The Center for Atomic, Molecular, Optical Sciences and Technologies is actually hosted by the IIT Tirupati as well as the ISER Tirupati. So it will be a great privilege for both the institutions to have you in Tirupati sometime. So
yeah,
you should.
No, I mean, I've never been to India. I've been invited many times, but usually it comes at the wrong time, of the year. Just so it has never worked out. But one of these days, it's definitely on my list. The things I want to do.
Well, it will be the right time when you come.
So, yeah.
So, Sunil, we are almost ready. We have another couple of minutes, I would think.
Yes, sir. Yeah. 2 more minutes. It's for 6:30, the scheduled time. Yes.
Yeah, so we will wait another 2 minutes and then we will be all set to go.
Yes.
Okay, good. And so you will just give some introductory words, right? Or somebody will say.
Right. Basically, yes. I will be inviting Dr. Arvind to introduce you.
Okay.
And after that, your talk will begin after Arvind introduces you.
Okay.
So we are about to start in another less than 2 minutes, I would think. But it's nice to have checked that everything, the whole technology is in place and connections are stable, they are working.
Yeah, we'll be in good shape. So.
Professor Bartschat, are we ready to start?
Anytime.
Sunil, Arvind?
Yeah.
Yes,
so
yes, sir.
let's start.
We can start.
Yeah.
Yes, so a very hearty welcome to everybody over here, especially to Professor Klaus Bartschat, who is a very distinguished physicist who has contributed enormously to the field of atomic and molecular physics, and everybody who works in this area would have come across his works. So let me invite Professor Arvind Gopalan from IIT Madras to introduce Professor Klaus Bartschat. Arvind?
Thank you, Professor Deshmukh. Good evening, everyone. We are very glad to have Professor Klaus Bartschat as today's speaker for the CAMOST seminar series. Professor Klaus is a Ellis Nellie Levitt Distinguished Professor of Physics at the Department of Physics and Astronomy at Drake University. After his PhD in habilitation at the University of Münster, Germany, he joined the Drake University as a faculty in 1987. Since then, he is a faculty there at the Drake University. His research interests include electron-positron scattering from atoms and ions, heavy particle collisions, photoionization, including the strong field processes in atoms and molecules, and also general scattering theory and computational methods. He has published 3 books and has several book contributions and invited review articles as well as several peer-reviewed articles. He has many honors. He has received many honors. Notably, he won the Will Alice Prize in 2016, and he is also an elected fellow of the American Physical Society. Today, Professor Klaus has plans to speak on how the fundamental processes of electron collisions with atoms and molecules and ions will empower our technology. So, without taking much time, I would like to invite Professor Klaus to take it on. Thank you.
Oh, well, thank you very much for the very kind introduction. I hope I can live up to what you just said about me. So, yeah, good evening in India. Good morning in case you joined from the US. And I don't know what time it is. It's late in Australia and I think middle of the day in Europe. So, yeah, so here's my talk. I think you can see my slides. I have to look to a different screen to see them myself. So when you see me looking somewhere else, it has to do with the fact that I'm looking at my slides. So that's the title of my talk with some contents. Tells you a little bit about where Drake is in the middle of the US pretty much. And before I really start, I need to acknowledge 3 people in particular. So one is Oleg Zazarini, who was a long-time collaborator in my group, unfortunately passed away 2.5 years ago. And I will show a lot of his work on the so-called B-spline R matrix method. And then, of course, there's Phil Burke, who was sort of my unofficial PhD supervisor. I did my PhD and my habilitation and all that in Münster in Germany, but I was very fortunate that my supervisor at the time sent me over to Belfast, and I had the great privilege to work with Phil, who is just a genius in this field, and I learned a lot from him. And then there's Catherine Hamilton, who was a postdoc with me during the COVID years, and she got her PhD also in Belfast. So we are sort of, we grew up in the same environment when it comes to numerical AMO physics. And Catherine, well deserving now, has her own assistant professor position at the University of Colorado at Denver, and I predict that she will do really well. Well, she is already doing well, but she had a phenomenal start there already. So I was going to talk a little bit about, to make it general, why do we do fundamental research, and why is this useful? Years ago, I was at the Gaseous Electronic Conference, and I presented some beautiful stuff that I thought was just great about spin polarized electron angle differential and whatever. And John Giuliani from the Naval Research Lab came to me and he asked this question, why don't you do something useful? And I kind of thought, oh, what do you mean by that? Useful? Yeah, he said, you must have total cross sections. Why don't you publish those too? And of course we do have total cross sections. So then I, wrote a paper with Mark Kushner, whom you may or may not have heard of. He's an electrical engineer, essentially. And the idea there was that they wanted, some years ago, they wanted to build basically a good laser with a bad laser as input. Let's just leave it like that. it involved cesium, but many, many other things as well. And so this is sort of a principled scheme, no big deal. I should say I'm willing to make these slides available via a link. So if you don't get all the links and it goes too fast or whatever, don't worry about it. You can have it, you can look at them, at the comfort of your home later on, and then find many references to various talks that I gave. So coming back to this, that's what they wanted to do. And then they showed us the scheme thus for cesium, and they needed data for cesium. A lot, to say the least, right? Far, far more than you can possibly measure. And then, I mean, it's not just cesium. It turns out that they also need helium. Then they needed, then they needed nitrogen in various states. Then they needed nitrogen molecules and even, some kind of small cluster type stuff. And it was just overwhelming. We couldn't provide all of it, but at least we did the job and we gave them whatever they needed for cesium. And I will get back to this problem later. But there was an interesting talk that I found at the recent ICPE conference in Ottawa, in Canada, by a guy called John Scheel, and he works in Amsterdam. So these are not, he kindly let me use some of his slides because I thought this is a good thing to have, because this is nanolithography, right? We all want to make computer chips, the smaller the better. And one of the things that go into is, how do you make these chips that go into your cell phone and all kinds of great things? And so there is sort of a critical dimension that involves the wavelengths. And so over time, what has happened is that they make the wavelengths smaller and smaller and smaller. And now we are sort of in this extreme ultraviolet region. There's the magic number is 13.5 nanometers. And the thing is, where does it come from, right? And it's used in these edging things. He had beautiful movies about it that I can't play. But it was this sort of, I was fascinated by the pictures and that he showed. And you have these tin droplets and somehow a very, very hot plasma, and that stuff comes out of it, right? And now what? And so there it is. There is this tin, or the ions of tin emit very strongly just in this wavelengths that they want. And it turns out, according to these people who know something about it, if you can increase the efficiency of this process by 1%, which isn't a lot, but if you can, that's worth potentially $1 billion for whoever company can do this. So it is worth studying this process to figure out how you may need to twist various parameters in order to do that, right? And so it turns out that this is absolutely phenomenal. So very, very, a large number of states, manifolds in this tin at various ionizations levels goes in, singly excited, doubly excited, triply excited, absolutely phenomenal. No way you can measure all of it. So they are relying on calculations, but I will get back to that. It's not so simple. Again, more and more excited configurations goes in, and then they do what plasma physicists do with these data. We don't know much about what they do with it, to be honest. They calculate some kind of average distributions and do whatever, but they have a lot of modeling to be done. So I think by this stage, I hope I could convince you that it is worth to look into the production and then also the assessment of atomic data. So it's clear they will be used for a lot of things, right? In plasma physics, modeling purpose, astrophysics, planetary atmospheres, you name it, somebody needs atomic data, right? How do you get them? Well, you get them, of course, the original way is you do experiments. Well, first of all, that's expensive. There's no doubt, Now, many of the ongoing experiments, in order to get, funded, for example, by the National Science Foundation in the US, you need to come up with sort of some new physics, not the useful stuff, the more exciting, sexy stuff, spin polarized, angle differential, and so on, right? And the other problem is that it is difficult, very difficult experimentally to measure absolute cross sections because of the normalization. I'll show a little bit about it, but that is generally a difficult problem. The energy and angle dependence is much easier to measure than to nail it down to what is the number at 10 eV and 25 degrees, let's say. The actual number well defined, and that's what needs to go into the models. And so then, of course, you can do calculations. And I mean, we do this for a living, right? And there have been huge projects, and they're going on. Mike Seaton in the mid-'80s, when I was still a student, I listened to Mike when he started this opacity project for astrophysical observations that was followed up by Iron Project. These calculations are cheap. They get cheaper by the minutes because computers get cheaper. Almost any transition in principle is possible, but the trouble is that there are methods, usually they are designed for particular energy or even angle ranges. And unfortunately, many of the cross sections don't do what the theorists would like. That means they don't peak at high or low energies, they peak somewhere in the middle, and that's the hard part. So then this is a very common method, believe it or not, and it's still a very common method, is that people simply guess cross sections. These applied modelers are extremely good at this. People like Mark Kushner, whom I mentioned earlier, he told me stories. It's quite amazing what they can do. People like Alex Dalgano, who was also a famous astrophysicist, of course, at Harvard. And I had the fortune to work with him sometimes, and it was just amazing what they could do. And there are people who claim that they can guess the cross-section better than anybody could possibly measure or calculate them. So at the end of the day, it turns out also that when you look at the results, either experimentally or theoretically, they are often wrong. And sometimes they are pretty obviously wrong. And even more times they're inconsistent. Now, of course, you have to be very careful when you say that for a concrete example to one of your colleagues, because it may have been one of your former friends, because they don't like this. But sometimes that is the reality. When an independent observer could tell that whatever number is published isn't most likely is not correct. So the question, of course, is who is right and why, right? And one thing I should say is, I mentioned it again, for a complete plasma model, you need what one would call complete data sets. Means you have a data set that can do, that you can use in modeling, and it doesn't have any holes in it. So you don't need everything, but you need all the important processes. And if these processes involve, for example, transitions between excited states, ionization of excited states, then often experimentally you are in trouble because it's not easy to measure these at all. So now let me give you an overview of what people have done. Again, this is now the fundamental aspect. I will tell you something about it and give you some examples of sort of what we have done, and then show how it connects to the world outside, how people are using these data. So again, when you look at the computational approaches, there are many, many around. And you have to really think about which one is the right one for you. How predictive is it? How accurately do you need the data? Often we go to conferences and people say, oh, we want these data. And then you ask them, well, do you need them to 1% accuracy, 10%, a factor of 2? And amazingly enough, often they don't really have the answer for that, which is quite amazing. So the question is, how much can you use from experiments, right? Do you trust it? Does your model have any predictive power? You might be able to reproduce experimental data with the correct input, but what happens if you change the numbers, right? So, and it depends on many, many things. Again, I don't want to read all the transparencies. Definitely, it depends on the complexity of the target. Helium, hydrogen, atomic hydrogen, of course, a favorite system for theorists. Unfortunately, as you know, hydrogen doesn't like to be to exist really as an atom, so more like a molecule. But helium is a good case. But if you want to go to radicals, to very big molecules, biomolecules, could be very tough, right? Then the question is, do you want to do the calculation yourself? Do you want to get a quick estimate, and so on, right? And which numbers really matter? That is not unimportant to know. And so then based on that, there are many, many methods. You have special purpose approaches. They can often do only elastic scattering and maybe the total cross-section. Optical model potentials are very common. I show you an example. The other possibility is Born-type methods. I used to, when I was a student, I had the fortune to work with Don Madison, who was one of the pioneers in distorted wave methods. Also, just heard people like Bob McEachran, Al Stauffer in Toronto. They did a lot of work. They are fast to implement these days very quickly. The question is, but there are some issues because they're not really first principles, because there is this potential that you can tweak to calculate the distorted waves, and one has to be careful about it. And then what I talk mostly about is time-dependent or time-independent close coupling. And again, you will find many, many abbreviations of what these are all called. So CC generally is close coupling. Then you put a number in here that tells you how many coupled states. Or people say convergent close coupling, R matrix. R matrix is nothing else than a numerical implementation of the idea. And the idea is simply you do what we learn in quantum mechanics. You expand your wave function in terms of a complete set of discrete states and continuous states. This expansion is very easy to write down and completely hopeless for a computer, right? So the classic case, a difference between theory and practice. So you have to figure out what to do with this equation. Again, there's a lot of technical issues. How do you do an infinite sum? How do you integrate over the continuum? And there's all these methods that have been developed, including ours. And there are some restrictions, but it turns out that one fundamental restriction that is very important for practical applications in complex atoms is the fact that they all like to use a single set of mutually orthogonal one-electron orbitals. That has a lot of technical advantages, but it limits what you can do. In principle, if you have infinite expansions, of course, it's not a big deal. But since you don't, and you have to approximate it, this can hurt you. And then there are time-dependent and other direct methods like time-dependent close coupling, exterior complex scaling. So you just do the brute force method and forget about any kind of expansions. You just go and solve the thing on a grid, on a space-time grid. Very expensive. The nice thing about it, you can kind of see how things developed, but it could be, and again, you will suffer from certain things that you have to do in order to make this numerically tractable, even with the biggest computers that are around. And then the question is, how do we treat ionization? And again, many, many different ways of doing it. A simple way, you put in an imaginary absorption potential that you hope is somewhat reasonable, and you kind of get it in some indirect way from something, right? You can do it in a continuum state in distorted wave methods, or you can try it directly on the grid, or in these convergent close coupling or R matrix with pseudo states approximations, right? Then you have to think about how important are relativistic effects. And again, there's basically three ways to do it. You can do a non-relativistic calculation and just recouple. You can do Bright-Pauli, you can do Dirac. it all depends. And now I'm just going to give you quickly a couple of examples to show sort of where we stand in the whole process, right? And so one is this optical model potential. Very common. Was the person who is really behind it is Gustavo Garcia in Spain, and they do a very simple thing that you can do in undergraduate computational physics classes. I did this last semester. You solve the 1D Schrödinger equation, of course, in radial coordinates, and there is your model potential, and you include whatever you need. Right? The static potential, that's easy, right? Then you start playing around and you don't use the actual potentials, which are non-local, but rather some local approximations that you can get quite easily. And we know they do sometimes a pretty good job. The problem is you just don't know exactly, when they might fail. But you do something for exchange, for the fact that the target gets polarized by the projectile. And then there's this absorption thing, right, that takes into account that there is inelastic scattering and everything, excitation, ionization, the whole thing is modeled by this one magic absorption potential. And then you go and do it. The result is, because you have a complex potential, now your phase shift becomes complex, and you actually get kind of 2-3 cross sections out of it, right? You can get the elastic cross section, you can get the total cross section, and that tells you that and we have checked this, and it is quite amazing. So about 12 years ago, we wrote a paper, and so this is what Gustavo's group gave. And, we nearly killed ourselves, let's say, and we thought that the best calculation that we could come up with is this red one. And it is quite amazing that the agreement was so good. We could hardly believe it, to be honest. There is one point for some reason is a bit off, but that's it. And they don't get this very low energy resonances. This is for electrons on iodine, which is not the simplest system. So it was really impressive, let's say. All right, then we have these people. The name was mentioned before this talk officially started, so not everybody might have heard it, but it turns out, people like Bob McEachran, Al Stauffer, they pioneered this polarized orbital method, and then they modified it and even included relativistic effects and also a little bit of an absorption. I was involved in years ago on that. But you see, if you look at electron argon, which is a very important system actually, and at low energies is very important. There's this Ramsauer-Townsend minimum, and I mean, it's absolutely beautiful, right? There's now experimental data that are recommended, and these guys are right on the money. I mean, that's it, right? So if that's what you want, good for you. And then it goes on, and now we have plane wave Born. Now you think, well, plane wave Born, we tell our students that's the last thing you do. If there's nothing else, try that. But then there was this very clever idea from Yankee Kim, who also unfortunately tragically died many years ago now in a car accident. And Yankee had this method that he knew when you calculate a cross-section for optically allowed transitions like that, it's too high and the maximum is too far to the left at low energies. So what do? Well, you rescale the whole thing and you move the peak, and you also take into account that you often know the optical oscillator strengths much more accurately than anything that you can get from collisions. And when you do this, so 2 little things, boom, he's right on the money. And he became also for ionization, he became the hero of the plasma and astrophysicists, because they could quickly get data from him. It was quite amazing. In fact, at some stage, he called me up and he said, "Can you explain to me why this works?" And I said, "No, I can't, but it's impressive that it does." And so it goes on. Semi-relativistic distorted wave. And so Don Madison tried this properly, and there is problem if you're not careful about it. Of course, the results depend, as I said before, they always depend on the wave functions you use, on the potentials. So things are kind of tricky, and then at low energies near threshold, there's another problem. Don didn't unitorize his scattering matrices, and so but you can fix this. In fact, Arati Dasgupta, who some of you may know, she works at the Naval Research Lab. She has a code that fixes this, and so that can be handled. But in some cases, it can be really wild, and you can see also that, I mean, it's all over the place, you know, for some excitation. I mean, what on earth is going on here, you know? So you need to have some kind of an idea about what matters, right? And of course, look at some of these experimental error bars. Well, you can say for a real diehard plasma physicist, a number like this with an error bar like that, we just put it as 0 and hope that it doesn't do anything. Then there's this time-independent close coupling, which I mentioned. Again, I don't want to go into all of the details. If you know it, you do. If you don't, 15 seconds is not going to make a difference. Here's the expansion that I wrote down at the beginning. And let me just tell you, the advantage of the method is that it can give you a complete data set, transitions between everything that you have, every state that is in this expansion, you can get results for. The other thing that is not unimportant at all is that close coupling gives you internally consistent results. That means it conserves the flux. We don't lose electrons along the way, or we don't generate them out of nowhere. It's a unitary theory, and for plasma applications, that is very important. So in fact, it doesn't help if you have 100 transitions and 5 of them you know exactly very, very well, but the other 95 are not consistent with these 5 that you had because you used different methods to get them. So it is better to be, or let's say it's most important. So if you are wrong, it's still good if you are consistently wrong. And close coupling can do that for you. So giving a bit of a status, this is now 25 years ago, electrons on helium is a very important problem, of course, for plasma physicists. When we talk about driving technology, I mean, we still need to do this for, if fusion ever gets going, really, helium data are very important. Fritz de Heer used to assess them on a regular basis for the International Atomic Energy Agency. And in 25 years ago, he already said, look, for those kind of transitions, the experimental error bars are too large. And so if you want to know it within 10%, just take the average of the 2 best calculations at the time. One of them was Igor Bray and Dima Fursa in Australia, the so-called convergent close coupling. The other one was our RMPS. And I think it's pretty convincing. So, but then, whoops, if we go to more complex systems, very low energy, very challenging problems. So again, we wanted to nail this and we couldn't. Steve Buckman had measured this 40 years ago when he was a PhD student or postdoc maybe. And there's resonances all over the place. So just remember this picture. I'll update it in a minute. So then comes Oleg Zatsarini. Again, I don't want to go into the details, a complicated thing called the B-spline R matrix method. The big thing is that I mentioned earlier, this non-orthogonal orbital business, he relaxed that. And then on top of it, he used B-splines rather than finite difference methods, numerically very advantageous. The problem is that these calculations are huge and we need a lot of computer time to do this, right? But is it worth it? Yes. So I should say, well, we did a lot of systems. And again, it's a general code, so we can take anything you want. I'll show some examples. it's interesting. I think it's 10 years old by now, but I think the main points are still in this topical review from 2013. Since then, we've done many, many more calculations. As I said, unfortunately, Oleg has passed away, and we're still suffering from his loss. But Catherine and other people, myself as well, try to kind of keep the legacy going, because it's just really some impressive thing. We need big computers. They get upgraded every 3 years. Even Stampede 2 is going to go out in 3 months or 2 months now, November, I think. So we have a lot of big machines that we run these things on. And this is one thing that Oleg showed me shortly after he arrived at Drake. We had done a calculation. This is for neon, where it's similar to krypton, not as bad, but Oleg was really right on the money. I mean, every single point on this curve, with one caveat, we had to take the entire experimental curve and multiply it by 0.78. So, of course, we checked with Steve Buckman, who had measured the data, and he said that is well within our experimental uncertainty. We just didn't know these absolute numbers. But remember, absolute numbers are important for applications. And then we worked angle differential on neon, beautiful. Then we did other stuff, indium. And you can see here is an example of how hard you may have to work. There are experimental data. In this case, for example, this is the relativistic distorted wave is hopeless. It is way off. In some cases, if the energy is high enough, you might be able to get the low energy, the low angle cross sections, but that's about it. Right? So one has to be careful with these methods. And then we checked convergence. So we do this all the time. So we really try to push this and say, okay, these are the numbers, right? How do we do ionization? Again, I don't want to go into the great details of this. That is probably not worth it. Just to show that it works, the dirty tricks that we apply. There has been a lot of discussions among, expert theorists. We had very friendly but intensive discussion with our Australian buddies, who are very good friends of mine, and at some stage wrote a little comment saying, we don't think that this works. But it turns out that it does work, and we all agree now that it does work. There's some magic behind it, but it does work. And if we can give these data, that's good. So again, we did a benchmark comparison on triple differential cross-section. And now you can see, I mean, this really is I think it is quite impressive. There are three methods now. The B-spline R matrix, Oleg Zazzarini, basically, convergent close coupling, Fursa-Bray, time-dependent close coupling, people like James Cogan at Los Alamos, and we've got it. I mean, it looks pretty good, I would say. And then we can even do these 3D things, so every angle, you look at it, and so nobody was anywhere near what the BSR method could do. So this is how they measured it in Heidelberg, and we published that. So it's a long story. So let's not worry about it. So come back to what do we do with all of this, right? So now we had this great, all these fundamental theorists, work like crazy, and now what? And so Leanne Pitchford, a couple of years ago now, she had this idea is, we need to make sure that people can use these data, and basically started a volunteer effort. There's almost no money behind it, called LXCAT. And a lot of people contribute voluntarily, like our friends at Curtin, right? We contribute, right? And others. Australian National University, Quantumol. Quantumol, I will talk a little bit about it, is a commercial operation. But nevertheless, so people help. Luis Alves from Lisbon, and so on. So lots of people. And so give you an idea, you can look at this. And so we didn't quite make the 20,000 mark. I didn't check this morning, but we must be very close. So those data, that this is an old screenshot from 2 years ago. So basically it has been downloaded roughly 15,000 times since then. So people are very interested in this. They also need differential cross sections, not quite as many, but again, this is where the data go, and this is what people who want to use them appreciate. So we have Quantumole. Quantumole is a commercial business. I'm on their advisory board, so I can't say too much about it, but they released a database of plasma chemistries and reactions. And as you can see, somewhere Catherine is on it, Oleg is still on it, and presumably I'm somewhere also on this. I should be on this. But anyway, okay. There it is. Okay, here we go. So, and they have all these processes. You name it, everything is there. They use not only atomic data, of course, molecular data. They use a lot the UK, so-called UKR matrix molecular code, UKR-mol or R-mol plus, which is, again, it came out of fundamental research, right? And now we get to the point is, how good are these data? And so there was a push by Gordon Drake, who was the editor of PhysRev A at the time, and they published an editorial and said, we need to assess the quality of theoretical data. There's a lot of numbers, but are they any good? And so we did this. And so you need to know structure stuff. What are you colliding with, right? We did oscillator structure work, a lot of structure work, thousands of transitions that went into models, right? And then we looked at various systems. So, for example, beryllium plus and beryllium. Those things are important, again, for fusion research, right? You may know they might try to make these windows out of beryllium, which is not the nicest atom to work with. So it's difficult, if even possible, to do experiments on it because it's so highly poisonous, and most universities or labs will not allow the stuff to be anywhere near your graduate student who you would have to sacrifice, basically. So those are systems that we can solve about 20 years ago. And, again, if you use the wrong method, you may be way off, but if you use the right method, we can get it. And, now one can, for systems like that was driven by Yuri Ralchenko at the National Institute of Standards and Technology in the US, who publish databases and do things. Again, for the general public, you see, there it goes, and we published this paper, and it's basically, you can do plasma physicists often like a fitted cross section. I mean, it's perfect, right? For some crazy transition, a triplet D, singlet F, nobody would ever be able to measure this, but we can calculate it, and we are convinced it's right. And so on, right? And then now you go, this beryllium, but what about astrophysics? Iron, about good luck with iron. This is just to give you some ideas about the crazy spectrum of ions, just a discrete spectrum that you can find. And then the calculation that Oleg did, and then compare the experimental energy values with the NIST database. And so we need the energy structure of iron plus for the collision. And for the initial bound state in photoionization, you need neutral ion. And it's incredible. And then you get a mess like this, right? But you won't believe how excited the astrophysicists were when they all got that, right? Looks like the sun only shines because of these data or whatever. So it is really an interesting situation. A lot of data, Again, you can read the paper. I just want to show, how crazy this is. Of course, you can calculate some thermal averages, but just to get the average of all this correct with these lines is a major challenge. And of course, astrophysicists are not the same, right? So we work with our colleagues in China. You know, I really like the fact that physics still is, or at least AMO physics, where we don't do weapon research directly, is still pretty open. You know, we have friends all over the world, independent of what our politicians tell us whom we have to like. So Yang Wang was at Drake for a while, and I've been at Harbin a couple of years ago now for a while. And so the idea there is they want to build thrusters based on xenon and to getting electric propulsion devices going. So we had one paper on that, and we did what you do. You could, first of all, you do a calculation of, you know, are your data any good? Okay. And we found out, yes, they're good. And then we do modeling, right? And so we model. Next thing is we have a second paper. So now we're using these, you know, so we actually model these Hall thrusters. And of course, we get help from people who are real diehard plasma physicists, right? Jiming Zhou was a long-term postdoc in Uwe Czarnecki's group at Bochum, and I've known this group for a long time. Third paper is almost published. And so what about the really, really heavy complex systems? You know, as you know, ITER under construction in France. We never know if the darn thing gets to go, but if it ever works, there was a meeting at the IAEA in Vienna, International Atomic Energy Agency, and the guy says, you know, there's three important elements in this world, and they are tungsten, tungsten, and tungsten. And now the next slide shows you the best results that we have so far for tungsten. In case you don't see any, that is because we don't have any. It is an extremely complicated system, and we have to work on trying to somehow get this thing to go. A lot of work is required, and clearly there will be collaborations between theoretical groups needed, and also between these groups and the ones who ultimately want to use the data. So the next thing is, you know, you can say, can you just do it yourself? Or as you may have heard, there's these ChatGPT. Can ChatGPT do it for you? So when you want to do it yourself, you have various possibilities. So for example, you could try, in the old days, it was possible to go to Los Alamos and actually do it using the Cowan code. If you try that now, unfortunately, due to security issues, you will get a slide that or a screen that looks like this. So it's unfortunate. Yeah, then you can do other things. For example, this FAC, the flexible atomic code, very interesting. I wasn't able to check it. But I did the download, and it worked somehow. There are other things now. Stefan Fritsche has, they are working on this, what is it called? Jena package, which also is sort of uses some symbolic a language, you know, say the high level language like Julia, and to make the input as simple as possible. And you might actually be able to do it yourself using that way, right? And the other thing I want to mention, very important, is this atomic and molecular and optical gateway. And we really hope that that will be a winner. It exists. I would highly recommend that you take a look at it. There is a bunch of codes are now available, top-level codes with convergent close coupling, BSR is somewhere here. Where is BSR? It's over here, right? R matrix with time dependence, if you're interested in laser atom and molecule interaction. There's the UKR mol plus. There is a polyscat, which is for big molecules, can only do elastic scattering, and so on. T-Rex, you name it. There's a lot of interesting stuff around. And fortunately, we just got funding for the next 5 years with a significant amount from the US NSF, about $2.3 million. So that should help us to keep it going. There's an interesting link. Catherine gave a beautiful talk at the GEC in 2021. Again, it will be, you can do this link and you can find it. And if you're interested, I recommend you listen to it. So let me come back to this loop that I started off with. What happened to the cesium project, for example, that I mentioned? So we give them a large amount of data. Well, Mark's group does whatever they do best. They do something with these data and many others. And the result is that, unfortunately, they found out that after so and so many shots with this laser that they wanted to build, that there's too much cesium plus coming. That was the killer. But it turns out that it was a whole lot cheaper for them to pay us some money to do these calculations for cesium than to actually try to build this laser and then find out that it doesn't work. So it's one of those examples. So that unfortunately didn't do the job. Now, back to this tin problem that I mentioned very early, right? Again, this is from John Shields' slide. An absolutely amazing list of configurations they have to do. And then, of course, the Los Alamos people did the calculation because they, of course, can, are authorized to use their own codes. And James Colgan did this, and they got these results. And they are quite happy with it, and they keep working on it. So this is a clear case of, those kind of calculations at the end of the day will be important for, possibly important for the next iPhone or whatever there is. Maybe there's other companies, Samsung or whatever, who makes these cell phones, and they're trying to get smaller and smaller chips, and they make them cheaper and cheaper. So that's what they got. I mean, it's pretty impressive, I would say. There's some modeling. The theory is this. There was an experimental test on this. I mean, of course, there's a lot of averaging going on. I'm sure they won't be able to nail down individual transitions, but apparently this is it. So again, as I said, so a 1% increase in efficiency of this could get you $1 billion for the company who manages to do this. So there is economic impact, and it relies, there's no doubt about it, it relies on having some underlying fundamental AMO data, experiment, and theory in order to achieve that. So, well, I'm already coming to the end of my talk. It looks good. I was told 50 minutes, so I have about a 1. So, I mean, I think it's kind of clear. These collisions are a vital part of atomic and molecular optical physics. The field is mature, which is sometimes a criticism, but they need the data. We have lots of fruitful collaborations between experimentalists, theorists, users outside of AMO who need and use these data. Of course, experimental benchmark data remain important to test and push theory. We shouldn't just rely on that. We do need to make serious efforts to estimate what the uncertainty of these data is. Can we live with them? And if not, so we must, as we wrote in that one topical review in JFISH-D, I think it was a very good idea that was pushed now, and you can't publish in PhysRev-A anymore now, or in PhysRev in general, unless, as a theory, unless you have some indication about whether or not your data are any good. So there's clearly, I didn't have time to do this. This was not the topic of my talk. Even though we do very complex calculations, there is room to try and see what the whole thing all means. But I didn't have time to talk about that. Machine learning is another topic. I didn't have time to talk about it, but that is something that also comes up now. And I predict this will have a future where, again, you let a computer try to figure out or make some sense out of some kind of learning data set, and then try to get cross sections and whatever other data are on there. Of course, there needs to be interest from these agencies, both those like the NSF, very fundamental, NIST, more fundamental, but also Department of Energy, Department of Defense. These are US agencies, but wherever we are, right? Or you can wait until ChatGPT can do it. Maybe version 6.5 ultimately can do this for you. If you want to contact us, these are, again, the most promising emails. Catherine is, as I said, now at Denver, but we are in permanent contact. In fact, right after this, I'm going to talk to her about the gateway. Of course, sometimes, we do what we can for free, but in case somebody wants us to do a new calculation, we will have to ask potentially for some money. And so this has happened. There's only so much one can do. So with that, I thank you very much for your attention. And this is the end of the talk.
Wow. What a fascinating talk. And how challenging it is to use various approximations. Ritesh, maybe you can take over for the question answer session.
First of all, thank you, Prof. Klaus, for such a nice talk on highlighting the importance of atomic molecular cross sections in technology. So the floor is open for questions. If anybody has questions, please raise your hand, or you can just turn off microphone. Yes, Arvind.
Yeah. Thank you very much, Professor. It was a very nice talk. I have a question about this. You have data on electron collisions with atoms and molecules. What about clusters of atoms? Is it
that's really, unfortunately, not my field.
okay.
Even molecules, I've stayed away from all but the simplest molecules. I always, my joke is always to say, how do you spell molecule? And the cluster situation is tricky. There are people who do this, but of course you need to make models. Often they do it in some kind of, there's more classical things involved, and it sometimes works, and people also have these, they see what happens, for example, if you put an atom into an environment, so these are very important topics. Unfortunately, I'm not an expert on telling you any details about this. I realize it's important. If I see a grant proposal and I have to referee it and it's a good proposal, I will say this is important. But unfortunately, I'm not an expert on what exactly you should do, right? Again, but you can certainly put an atom into an environment. People come up with relatively simple forms of modeling that environment via an additional potential and boundary conditions, right? But I don't know the systematic data sets that are available. You would probably have to contact those people who actually do these calculations.
Okay. Thank you.
Yeah, Bruce, I have a question. So in your calculations, how important is the relativistic effect? I think in this electron atom collision study that you have done.
Yeah, well, this depends a lot on the system, of course, right? There is a general rule: the heavier the target, the more important it is, right? But this is really a very, very general rule, because if you think about, just compare neon, which has Z equals 10, and sodium, which has Z equals 11, right? Sodium, in most cases, is non-relativistic. It's like hydrogen with a little modification for a core potential, and you don't have to worry about it. But neon already is what Tim Gay, one of my friends from Nebraska, would call it the devil's atom, because already neon, the discrete states, all the excited states of neon, 2p5 NL, do not well LS couple, because you have the core split 2p, the 2p5 has a significant doublet P 1/2, 3/2 splitting that you can see experimentally quite easily. So it depends. It's very hard to tell for the very, very complex atoms, certainly like, as I mentioned, tungsten is a killer. Sometimes people overestimate of how important it might be. This depends on how much averaging the modelers are going to do with these data, right? This is the classic case of how much lumping are they going to do, right? If they do a lot of lumping, so if the modelers treat the entire fine structure manifold, for example, as one state, chances are you don't have to kill yourself to get them all individually correct, because somehow summing and averaging is going to help you out.
Yeah, sure,
so it's a little bit difficult to tell in some of these very detailed experiments, definitely, because if the experimentalist resolves the fine structure, then you better do it as well, right?
Yeah, Professor Klaus, I had one more question. This is a little bit basic, like, you mentioned about the time-dependent calculations. So electron scattering. So the time dependence, so how do we include it? Like on a perturbative level, the interaction is time dependent. That's how we do it? Or is that
what they do is, this is the thing, if you do standard electron atom collisions in a steady state situation, right? You learn in your introductory modern physics class already that this is really not a time-dependent process.
Correct,
right?
correct.
It looks like it, but it isn't, right?
Right.
Because the time dependence is somewhat trivial.
Right.
So, however, the advantage, of course, is, which we also teach. In fact, I'm going to do that tomorrow morning. The advantage is that you can kind of see what happens, right? You see this wave packet running on the atom, and then, it wrangles the whole thing up. And something will happen, and at the end, something might be reflected. These simple problems, even with boxes, and wells and more. So you can see some stuff.
But in that case, the interaction potential is still time independent, right?
That's correct. that is the whole point, right?
Yeah.
So nevertheless, these calculations can be done on a grid, and they are very different. And so people. The thing is that, for example, in these calculations, you have an initial state, you propagate it, and then you have a final state. And instead of doing these expansions that involve physical states and pseudo states, you can simply project on to what's known the correct asymptotic states. That's one of the advantages of this. Right, you don't have to do these tricks and trying to project onto unphysical states. For example, these pseudo states they might have positive energy, but they are not real continuum states, right? So in E2E, for example, in ionization experiments, when you do this, you project on states with the wrong boundary conditions, and you just hope for the best, right? In the time dependent, you don't have to do that. But I have to say, in standard electron collisions, what I was talking about, these methods have kind of run a bit out of favor because they can only do relatively simple targets. And at the end of the day, it is an overkill. It's nice to see the results, but now, of course, there are other things which I didn't have to talk about. You have to invite me again, and then I'll give you a talk about time-dependent stuff. When you look at our matrix with time dependence, then you really have a very strong laser, a short pulse laser, and then, of course, the only way you can do it is to brute force. Having initial state, and you just go for it, right? You propagate the initial state in some big laser field and short pulse, usually, because long pulses will kill your computer, So it's a different ball game, right?
Yeah, thank you.
But you're completely right. The interaction potential is time independent. In the standard collision, it's a standard steady state, so you don't have to do a time-dependent calculation, except for if you want to see the physics and for ionization, get
a
bit easier to get onto the correct boundary conditions.
Thank you.
Okay, Professor, I have one question. So as you mentioned that the measurements are very, very limited. Perhaps, let's say if we consider plasma modeling kind of application, then they are also not taking the full span of energy domain. They're usually available only on 3-4 energy range. Let's say if we talk about total cross section. And then if we look at the calculation side, we get perturbative approaches, cross section, we get non-perturbative. Then in non-perturbative also, we realize that cross sections are limited in the sense, in terms of transitions, where if you look at plasma modeling applications, you need enormous transition data, most of the cases. And many of the times comparison come good. If you try to compare, many of time it doesn't, but in the absence of measurements, or considerable measurements, particularly at low energy, there's not much data. How a person who is doing the plasma modeling should go ahead and try to, let's say, select the data, if there is any way we can, or if you're from your experience, if you can suggest something.
Well, the simple answer is they should use our data because they are correct, right? But that's a bit, let's say, arrogant. The idea was to, was the issue of Gordon Drake's push for a somewhat realistic assessment of the accuracy of theoretical data. I mean, you're right. As I said at the beginning, the perturbative methods are known. Again, that's what we teach. And it's kind of true. There are exceptions, one has to be careful. For high energies, optically loud transition, small angles, right? Then there's close coupling, which is typically was developed as a low energy method, right? And if you go back to Mott and Messi, the old days, I mean, that's it, two-stage close coupling, you know, things like that. But the idea really, and the person who needs, I think, a lot of credit for this, is Igor Bray from Australia, my good friend, because he came from gravitational physics, but for personal reasons took a postdoc position in Ian McCarthy's group at Flinders University at the time, and this was in the early 90s. And as you know, Igor and Andrei Stelbovich in 1992 published a famous paper about these convergent close coupling methods. But the philosophy was that Igor came to Ian McCarthy's group. Ian was a giant, of course, the Australian equivalent of Phil Burke, right? Ian told him, look, we have these high energy methods, you know, we have these low energy methods, and there's this optical potential thing, and we tried this, and so basically we know which method to use for what system. And Igor said, why is that? Why do you not have a method that can handle any energy, right? One method, all energies, all angles. And that was the idea of convergent close coupling, how it grew up. They learned about these basis functions, the Legendre functions that they use. And I mean, there has been a lot of developments. And it was very helpful also from Andrei Stelbovich, who interestingly was a nuclear physicist. In fact, he was at Münster as a postdoc when I was a student, but we didn't know each other. We only found out later. And it was good for two people to come from a different field and basically ask some fundamental questions about what on earth are all these, you know, theoretical collision physicists doing, right? Why are they so happy or content with the fact that we have particular methods for certain cases and a different method from another one, right? So I think you should look at, you know, these data, look at the people who calculate them, talk to them, and see if they can justify why their data set is the one you should use. I think I can make a case that for some of that you should use our data sets. I can also assess reasonably well that sometimes you should use others, maybe, you know. We have a good relationship, I would say. There's no competition, really. People, you know, we know each other's strengths and weaknesses, and fortunately, the situation is really very friendly. I mean, the Australians are, you know, some of my best friends. You know, I know, you know, James Cogan at Los Alamos, you know, very, very well. James was Phil Berg's last PhD student. So this is all, you know, these are all going back to, I mean, Phil Berg built an enormous empire and of people, and somehow he was a gentleman always. Phil could have tried to block the development of CCC, because at the time it was a direct competitor to his R matrix method. But instead, he supported us as well, because BSR was another competitor to the R matrix method. And I think it is very important that people collaborate instead of trying to, you know, keep the other group low.
Maybe if you allow, I have one more question. So particularly what I experienced in plasma modeling, rather than comparing the cross section, if one go for more kind of a parameters, let's say rate coefficient, which is average over electron energy distribution function. Because if you talk about plasma that actually generate in, let's say you can have a plasma with 1 electron volt and higher also if you talk about ITER. So rather than if we compare the cross section calculated from different methods, if we go with like more quantity which right away goes in the plasma models, like say rate coefficient corresponding to those processes, and if they are reasonably agreeing with the methods, maybe that could be one of the way one can maybe sell. I was just saying if what you think, maybe that that's what I do normally when I am confused.
No, I mean, of course, you know, when you look at rate coefficients, you know, occupation numbers and things like that. So there is some additional, you know, integrations, averaging going in, chances are that then the numbers get closer, right? And if this is good enough for your plasma model, then it's a lucky case, right? But it's not guaranteed, right? So yes, one should do this again. It comes back to some of the stuff that I said. You know, it is important to know, you know, which numbers do you actually need for your plasma model, and what accuracy you can get away with to get, you know, results that ultimately reflect what Mother Nature thinks about the whole thing. Right?
Agree, very well agree, sir. So any other questions from any participant, either online? I check on YouTube also if there is. No. So maybe we can conclude here. Thank you, and I request Prof. Deshmukh to please give the concluding remarks for the talk.
Well, thank you, Ritesh, and thanks to everybody. Professor Klaus, it was a very enjoyable talk, so much detail in it. It was really amazing, and we will like to have you visit India sometime very soon. So please keep that in mind and do spend a few days at Tirupati.
Thank you very much. And as I said, I will send you and I think Aryad, I'll send a link to this Dropbox file, and then you can download.
Oh, absolutely, absolutely. That will be very useful. Yes.
Okay. So, then I will sign off now. All right. Bye-bye.
Yes. Thank you, sir.
Thank you. Goodbye.
Okay. Bye.
Thank you.